was also a teaching researcher at the Polytechnic University of Milan, Italy, in 2015, and the Technical University Turkey in 2019. He was also a
சார்
in
சிட்டி பாபு சார்
Yes, sir. Yeah,
கணேஷ் குமார்
please.
சார் சார் பின்னாடி பஸ் சவுண்ட் எல்லாம் கேட்குது சார்.
Yeah, it is because I am staying in hotel, sir. That is what.
Okay, was because lot of full bus sound is there. Any possibility to close the door?
Yeah, but it the signal problem.
Oh,
he was also a recipient of a prestigious young
in
scientist.
presently it's okay, sir. Okay.
Yeah, now I closed the door, but network may, I mean,
Okay,
network may disturb. Okay, let's see. Yeah, okay. Is it okay now?
It's okay, sir.
Okay.
He was a recipient of prestigious Young System Scientist Award 2019, which is sponsored by System Society of India. Sir has also served as an editorial board member of many peer-reviewed SCI index journals, including IET Renewable Power Generation, IET Power Electronics, IET Energy Systems Integration, etc. Sir has also published over 50 papers in SCI and Scopus index journals, including IEEE and IET. His research areas include power electronic applications in smart distribution grids containing renewable energy sources, design of low power photovoltaic system including MPPT algorithm, and control and grid integration of renewable energy systems. Sir was also a senior member of IEEE Power and Energy Society and IEEE Smart Grid Opportunity. A warm welcome to you, sir. We are happy with you here for accepting our invitation and delivering the lecture over here. Thank you, sir. Over to you, sir.
Okay, yeah, thank you very much, Dr. Naresh and Dr. Saravanan, and who was invited me. Yeah, who was invited me to, I mean, give an invited lecture for this proposed ACT sponsored STTP. So thank you very much again, and this is my second time I'm giving a lecture for this ACT sponsored STTP, hosted by BVRIT. I mean, thank you very much, Dr. Saravanan, and giving me an opportunity. Yeah, thank you. So it was a privilege for me, sir, to share my knowledge in this area of grid interactive solar PV system and with participants. And I assume that the participants are from the background of electrical engineering, power electronics, and power and energy, so that you can understand the concept of the grid-tied solar PV system. So I'm an assistant professor in AAA in Kanjipuram. So I have developed a laboratory called the Photovoltaic Research Laboratory, and is sponsored by DST ACRB. So I could take around 35 lakhs project for this grid interactive PV system. And we have developed this laboratory of 1 kilowatts grid interactive PV system, and our team is actively working on the grid integration of solar PV system. And this is one of the emerging area of research. The present situation that the renewable energy sources are playing a very major role for future energy demand, as well as mitigating global warming and the pandemic. This current pandemic situation. So as we are, interacting through online or the virtual session, really I feel sometimes it's a kind of uncomfortable situation to deliver a talk online because many parameters are involving, as you might be knowing. And the past couple of days, and there was a cyclone and near Chennai, and we are facing difficulty with the internet as well as the mobile network as well. So with that, I have committed this. And however, I asked Dr. Saravanan to postpone my session to this Friday, and still the network was not stable, and we are facing many difficulties. The participants may think in straight away that because usually the speaker has to give a lecture without any interruption, and we should understand. But it's beyond that, the many parameters are involved, and not only that, as a organizer organizing such online STTP and finding a resource person in a reputed institutions is very difficult. Okay, participants. So you please bear with me, as well as bear with the organizers as well as the speakers, because we are putting an effort to deliver a lecture for 2 hours and without any interruption, but still is very difficult. Okay, so please understand that. So criticizing the environment or commenting, ultimately you have to understand, as we are academicians. So what may be the difficulties? Maybe you are from different private institutions, so understanding the difficulties to work in this harsh situations is a very tough task. Okay, So hope the situation will become normal, and again we shall meet very physically. So I am here in TTM. So I have given a number of lectures, even in physical mode in NIT Warangal and NIT SV, NIT Surat, and NIT Jaipur and NIT Trichy. Many NITs I used to give a lecture. So it is good again we shall meet physically so that you can understand the effectiveness of this delivery on this grid-tied solar PV system. Okay. Yeah, and the outline of my presentation include renewable energy in Indian scenario and the objectives of the research and what we have done and the grid interactive PV system and how the hierarchy of grid interactive PV system has been made so that the power generated by the solar PV system can be used for a local load or maybe can feed power to the utility grid. And what would be the, the solar PV system architecture? How the design of different subcomponents have been made. Because as we have made it, in the laboratory prototype, as I have strong collaborations with the MNIT Jaipur and SVNIT, so we could be able to make such a dedicated control algorithm for a great interactive PV system. And of course, the research is a component that we are the learning stage to identifying the problem in this area is very difficult. So you should have strong collaborations as well as networks as well. To enhance your profile as well as to enhance your knowledge in the particular area of research. So network is very essential. And for this laboratory prototype of 1 kilowatts grid interactive PV system and how different subcomponents like a power circuit and control circuitries have been made and how experimentally that has been validated, because the experimental validation is a very one of the vital component in this area of research, because as we are not working any kind of algorithm based work like computer science or maybe an image processing background, but we are all electrical engineers, so the real-time validation is very essential to have a publication in very top notch journals like IEEE or IET. And we have come up with certain observations, and we have done both scientifically and mathematically, and so we could be able to validate the research in the experiment also. So what was the final summary from the proposed research? So it has come up with certain observations with the improved performance of grid-tied solar PV system, and how we identify the problem, citing the recent references as well. Yes, Yes, I'm audible. Participants, you please mute your audio, and if you face any difficulty, one can mute and tell me that, and accordingly I can understand that. Okay, so
sure.
Yeah, throughout the session, please mute your audio so that I can understand. So you're facing difficulty. Okay, yeah. Okay, yes, let's come to an important aspect of this lecture, renewable energy in India. Maybe many of the speaker might have given the similar the topic and the introduction, but still let me reference it yourself. With India is one of the countries with the large production of electrical energy, and moreover we are third largest consumers of electrical energy across the globe. As of 30 September 2020, so around 36% of the total installed capacity is from the renewable energy sources. Out of 373 megawatts of the total installed capacity, and during September 2020, and around 135 gigawatts of power has been met by renewable energy sources, including photovoltaic and wind, and apart from the large hydropower plant. And these two key technology, the wind energy conversion system and the photovoltaic energy conversion system, basically they are the energy sources most widely used for the large scale power generation system and to generate the power in terms of megawatts and to feed power to the utility grid. And the target would be around 57% of the total installed capacity from the renewable energy sources by 2021, according to Central Electricity Authority Government of India. So as 50% of the total installed capacity should be for the renewable energy sources. Yeah, obviously it is a very challenging task by the initiative by government of India, because as you might be knowing, around 80% of the energy, still we generates by conventional power generation like thermal power plant and hydro power plant and other nuclear and all. But now the scenario has been changed that this global warming and CO2 emissions, and moreover the depletion of fossil fuel. As you might be knowing that transporting these fuels like coal fire, coal or maybe petrol, and you might be knowing So at present situation, so it is very expensive, and moreover the capital investments are very huge to generate electricity. And that is what we go to find an alternative to meet the future energy demand. So of course, the energy is a very important commodity for the consumers. So we can't imagine the situation without electricity. You might be knowing, so as we faced, many difficulties during the past couple of days in Chennai due to, interruption of the power as well as the, internet. You imagine that how, as a human being, you could be able to survive, right? So there are two key technology, is playing a major role in the 21st century. So the first technology is the information and communication technology. Obviously, thanks to internet. So how it has created the strong, impact among the, the society. And the second is the material science and renewable energy. So with the development in material science technology, you can see that almost all the field of engineering has grown exponentially, especially the renewable energy industry. So it has been, promoted like anything in this 21st century. Right. So the Indian, as I told you, that the Indian renewable energy sector is the fourth most attractive renewable energy market in the world, and third largest, electricity consumers in the world. And it is hold, the top fourth and the fifth rank in wind power and solar power respectively during 2018. But with the strong investment by the government of India, so it has been ranked top third in the solar power, in the international energy market, right, according to Renewable Energy Country Attractiveness Index by 2018. So with that, we promote renewable energy. Even many states like Andhra Pradesh and Telangana, the government has invested huge money for, the water pumping. The solar water pumping with isolated system, as you might have seen, and like Gujarat and Rajasthan, the government has taken an initiative for the street lighting based on the solar PV. So starting from very small scale power generation up to multi megawatts, you can find the solar PV system everywhere. Even the recently in Canada, Canada, they are going to install a power plant. It's about I think 2,000 megawatts of a very big, the solar power plant in Karnataka. So the government has, invested a huge amount, for another couple of decades, to promote the photovoltaic. And if you see that the development, before 2010, this wind energy was, it's holding top rank, especially in Indian perspective, we were in the top 10. So now that scenario has been changed. We give much importance for the photovoltaic power generation, because it can be easily installed at any site, as you might be knowing. Even we can have a mobile, the calculator with a small solar cell, solar powered calculator, or even you can see the solar powered toys, or solar powered smart watches, or solar powered, the electrical appliances. So as from microwatts level up to megawatts level, you can find the solar, cell for, energy production, because of that the very compact and very smaller in size, and it is highly portable, and moreover the power generation is very static. So that is what. So this, the photovoltaic, power generation is, it is emerging. Nowadays in the countries like India, or even Malaysia and Singapore and Bangladesh. So almost all the countries, they have started to harvest energy from this solar photovoltaic system. And this the installed capacity, as I told you, the wind power generation and the solar generation, basically they are the large scale power generation system to generate the power in terms of megawatts level. And we equally generates power by wind power as well as solar power. Around 38,000 megawatts of power, by, wind power generation system, and 36,000 megawatts of power by solar power generation system as of September 2020. So out of 89,000, 229 megawatts of power. And you can see the level of biomass power generation and waste to power, and still, and these two key technologies play a major role for large scale power generation. And as, the target would be, 175,000 megawatts of power. 175 gigawatts. By, 2022. In next couple of decades, and we hope to install the total installed capacity of renewable power generation would be 175,000, megawatts of power. So in solar power in India is a fast developing industry. As I told you, the country's solar installed capacity was around 36,000 megawatts of power by 2020. And as I told you, the among two photovoltaic and wind, the photovoltaic power generation system is the most promising and green and clean power generation system. And it almost it occupies, I mean, in the energy sector, it is playing a very major role in the Indian perspective. So the major advantage of photovoltaic power generation system is basically the installation, design, and starting up a new plant is very easy. So the investment time would be, I mean, it's very easy as compared to the wind turbine or maybe I mean the other conventional power generation like hydro and thermal. And moreover, and we may not think about the hydro in India that you know the I mean the scarcity of water and that is the very I mean the community is facing and right now. So most widely we use coal-fired power generation system to meet the I mean total installed capacity. And now we find an alternate that the solar PV system is one of the viable solution for meeting I mean future energy demand as well as mitigating global warming. And moreover, the PV generation system or the PV cells are highly modular. And you might have seen there is a very small solar cell can be embedded in your calculator. And as it is a solar powered calculator, I can find the solar powered toys, right? So it's highly modular. Hence, the plant economy is not strong function of the size. That is what. So thanks to material science. So as the with the development in material science, the solar power industry has gone to the great extent with the development of advanced materials for fabricating solar PV cells. And moreover, the beauty of the solar PV system is that the power output characteristics are well matched with the peak load demand, as it has an exactly the the bell-shaped characteristic curve. So that during hot summer, as the temperature and the irradiation is at a very high level, so you can be able to generate the maximum power by the solar PV. So you can meet the peak demand during hot summer. So with this objective, during 2012 Ministry of New and Renewable Energy Government of India, so they have floated and the call for proposals across Indian scientists with the title Hybrid Energy Systems, especially the hybrid wind and solar PV system. So that was an emerging topic during 2012. So they have floated. The main intention was that as an electrical engineer, as a scientist, working in the Indian institutions, so they should be aware of the fundamental characteristics of the solar PV. So how it well matched with both base load as well as the peak load. And if you talk about the wind turbine system or wind energy conversion system, so they are best matches with the base load and demand, and PV or solar PV system is well matched with the peak load demand. So throughout the year, by combining both the wind turbine with the solar PV, so we are able to meet both base load as well as peak load. So that was the intention. And moreover, it is a highly static structure as it doesn't have any movable part, obviously. So there is no, noise. It can easily harvest electrical energy without any noise as well as the pollution, and a high power capability per unit of weight thanks to material science, and the longer life with a little maintenance because of no moving parts, and highly portable because of lightweight. Obviously, it is very lightweight. You can see that the monocrystalline silicon solar cells. It is very portable. Moreover, it is lightweight, so it can be easily transported from one place to another place, and it also can be easily installed with limited manpower. And the value chain for the photovoltaic energy, as you might be knowing, so the solar cells are made up of semiconductor p-engines and semiconductor diode with using silicon. And silicon, as you might be knowing, it is one of the universal material for the semiconductor fabrication. So solar cell also uses the silicon technology for fabrication, and it has been fabricated from the polysilicon with the original material for InCard. So that will be fabricated with the silicon melting and InCard gluing. So we are vaporizing that the polysilicon material, so that we are able to build a PV cell or the solar PV cell. So with this InCard and the vapor preparation, so we are able to develop a PV cell, so that a single cell can harvest electrical energy in terms of DC with 0.5 volt around 25 milliamps per meter squared. So that is the size of the solar cell. So as you wanted to have a proper power rating to meet the load demand, then the solar cells can be connected in series parallel formation, so that we can build a PV model, the photovoltaic model with required power rating, and again connecting the different PV model in series parallel, and we can form a PV array, right, or the PV panel. So that can be installed in the maybe in the rooftop of your home, so that this may be a built-in integrated PV model. So other subcomponents are the associated equipments with the solar PV, is a PV inverter, because as the PV, PV cell is DC power source, and that generates a DC power, and that will be inverted into AC with the help of the inverter, so that can feed power to the equipments in the home, as well as the battery and the support monitoring and the system installation. So the basic concept of the PV cell, as I told you, solar PV cell is a single, PN semiconductor, diode with a heavily doped depletion region, and it has, the N-type material on the top of the, metal, and the P-type on the bottom. So it has been separated by the depletion region. So where this electron hole pair recombination occurs. So with that electron hole pair recombination, so it constitutes an electrical current due to the electron flows from anode to cathode, so that we can collect electrical energy to the external electrical circuit. So as the anti-material is exposed to the sun, so that the sun is a universe of energy, as you might be knowing. So all renewable energy sources are basically a byproduct of the solar energy, right? The sun energy. So in the solar cell, we use this sunlight. As there are in the state of sunlight is the temperature and irradiation, right? So according to the level of temperature and irradiation, we are able to convert that light energy into electrical energy in the form of DC, right? So the state of the sunlight are basically temperature and irradiation. That is what. So the light energy, as is exposed to the PN semiconductor diode, then light energy will be converted into electrical energy by the principle of photovoltaic effect. Then we collect an electrical current that flows towards the load. As the solar cell, as it is basically a constant current source when the voltage across the PV cell is low, and it is a constant voltage source when the current flowing through the solar cell is low. So basically it is a constant current source. We assume that the voltage across the PV cell is very low, about 0.5 volt. Right, so usually the electron flows is opposite to the direction of current flow. So what we assume, so that the current is pumped down from north pole to N to P. So that is in the reverse. And then it's like a battery, so that this can be a constant current source, so that that current can be feed to the load when it is when it forms a closed loop. Right. So as I told you, so that the solar cell or the PV cell is a constant current source, or maybe when it is short circuited, then the maximum current flows towards the solar cell. That is called a dark current, or maybe a photocurrent. So that the photocurrent, the photocurrent is the photocurrent. It depends on the irradiation or insolation. So insolation implies incident solar radiation. Right. When the solar cell is exposed to the sun, then the light energy will be converted into electrical energy with the help of the photovoltaic effect. Right. So the intensity of the solar radiation, so that decides the driving current, or that decides the photocurrent. So if the irradiation is high, ultimately the current is high, right? So at the zero voltage across the PN junction, the current would be maximum, and hence the current is called the short circuit current. And at the same time, when the current flowing towards the solar cell is very low, or the zero, then the maximum voltage appears across the PN junction. That is called the open circuit voltage. So the maximum voltage at the zero current. So this is what is called the open circuit voltage. That would be the maximum the voltage across the PV cell. So as the characteristic curve is highly non-linear. As the increasing the open circuit voltage, so the current decreases drastically. So voltage at which the current becomes zero is called the open circuit voltage. So basically it governs the non-linear characteristics, as it obeys the superposition theorem. So that the output power of the PV panel or the PV cell is basically the multiplication of short circuit current and open circuit voltage. Okay. So usually the voltage on the normal operating point of the any PV cell, it would be around 0.5 volt. Here it's about 0.5 volt. And in case of silicon PV, and the current protection of the photo current, it depends on the intensity of radiation called the insolation and the size of the cell. So if the size of the cell it would be bigger, then ultimately the current protection will be larger. But usually for the per meter square the size, the current generation would be around 25 milliampere, right? So you can see here, usually the maximum power would be extracted from the PV cell according to the characteristic curve. Here the point at which we extract maximum possible power. Because you might be knowing that any energy conversion devices and ultimately obeys the second law of thermodynamics, right? So whenever there is a transformation of whenever there is a transformation of the low quality energy into high quality energy, it is impossible to achieve 100% efficiency even in theoretical maximum limit. So obviously this, the solar cell, it obeys the second law of thermodynamics, and then the energy conversion is not efficient. Usually any solar cell can convert light energy into electrical energy at a very low efficiency, around 15%. Not even the commercial PV cell, not even 15%. If you could talk about polycrystalline solar cells, that is what. So the area under the curve, so the rectangular point, so that gives the effectiveness of the solar cell. That is called the area under the curve, that decides the conversion efficiency, right? So at the low irradiation, so the current is minimum. At the high irradiation, the current will be maximum, right? So the multiplying that current and the area under the curve, that gives the power production by the solar cell. And as the solar cell, it operates at the standard test condition, assuming the temperature would be around 25 degrees C, equivalent to 273 Kelvin, and the irradiation of 1000 watts per meter square. So that gives the corresponding rated current of the solar cell, and moreover, it depends on the cell size as well. So if the irradiation increases, then the current would be higher, and moreover, that depends on the solar insolation. I told you that. So the photo current is directly proportional to the intensity of the solar irradiation. So as the irradiation changes or increases, obviously the photo current increases. But moreover, the open circuit voltage, so it having logarithmic relationship with the irradiation. That is what at different irradiation, still you can understand that the variation of the voltage is very, very minimal. So in some case, we assume that the open circuit voltage is not varies when the irradiation changes. You can find the slight variation in the open circuit voltage. Okay, so that I told you that the normal voltage generated by the silicon solar cell, that depends on the type of material. For the silicon, it would be around 0.5 volt. And the PV cell technologies, as you might be knowing, basically the solar cell is a PN junction semiconductor, diode. It's made up of either any semiconductor material like germanium or silicon. As you might be knowing, as silicon materials totally dominated the electronic industry. As of still, it holds the top rank among all semiconductor material because it's naturally available and abundant, so that it is very cheap. And so even the solar cell industry invariably uses silicon, right? So silicon semiconductor, either it can be used in the form of crystalline solar cells or the non-crystalline silicon solar cell. And again, crystalline solar cell, that can be classified into single crystal and a polycrystalline, and having the energy conversion efficiency between 10 and 17% for single crystalline, and between 10 and 13% for polycrystalline solar cell. And the amorphous, basically a non-crystalline amorphous silicon cells, having the efficiency between 7 and 10%. And the compound semiconductor, even some, there is the research and development in the compound semiconductors. Mixing two different semiconductor material like a gallium arsenide or indium phosphide, and so we harvest electrical energy, so with the conversion efficiency between 18 and 30%. But still, it's a challenging task in the fabrication level to fabricate the solar cell. That's what still it is in development. Gallium GeAs based solar cell. And we have another semiconductor material like organic semiconductor, but still it is basically thin film material we uses. The conversion efficiency is very low. That is what the silicon solar cell is very popular. Choice for energy harvesting, and as it can have energy efficiency about 13 and even 17%. Now, and moreover, with the material science, development in material science technology, so they use multi-junction solar cell. So with that, still we can harvest electrical energy at a high efficiency, even around 30 or 40%. That's the way we use a gallium arsenide for fabricating solar cell. So basically, the conversion efficiency is the ratio between the electrical energy output and the energy of insulation of the cell. It gives the conversion efficiency. And the hierarchy of PV system, as the cell can be configured as a model, and the model can be configured as an array by connecting a solar cells in series parallel component. Series parallel combination. Each cell can have output voltage of 0.5 volt with between 5 and 6 ampere according to the size. It gives the output power up to 3 watts, about 10 centimeter size, and the model it would be around the output voltage up to 20 to 30 volt by combining more solar cells in series with 5 and 6 ampere. About power rating would be around 100 200 watts, about 1 meter size. Then further, this can be configured as a model, array with a power rating about 10 to 50 kilowatts, about 30 meter. See the hierarchy that the solar cell can be configured as a model of the panel. Again, this can be configured as a model, array. Then that can be installed in the plant for energy harvesting. So that is why. So as multiple of models are in series parallel, and again multiple of cells are in series parallel. So the reliability of power generation is very important here, because if any one of the solar cell is under faulty condition, maybe due to the external hotspot or due to very high temperature, sometimes it may damage the solar cells as well. That is why the reconfiguration of the solar cell is very important in before installation. So that is what the research and development is happening also in the reconfiguration of the solar PV model for maximum power extraction as well. And also the reliability is highly demanded here, that because if any one of the solar cell and under fault, and then harvesting energy and reliability, and moreover generating the same amount of power is a challenging task. So still many researchers are working on the reliability of the solar PV system, and again the degradation studies, because as the PV array is exposed to the sun, as you might be knowing, the performance is getting degraded if the solar cell is exposed to the sun at a high temperature, because any solar cell is exposed to the sun at a very high temperature, it can easily degrade the performance of the solar cell. So obviously the very high temperature, then it affects the performance, because ultimately that heat has to be dissipated, as it is the heat is developed in the PN junction semiconductor diode, so it can easily damage the devices. So that is why the what is called the degradation studies is also an important aspect in the solar PV cell industry. So many of the researchers are also actively working in the what is called degradation studies of the solar PV cell. That is why once you install a PV panel in a particular site, maybe after 5 years you can measure the temperature, you can measure the output voltage and current. Obviously, it is very less. Main problem is due to the degradation. So degradation that may be due to technical as well as non-technical reasons as well, because the PV panel is exposed to the it is sun, towards the open environment. Maybe the dust and the dirt will be accumulated over the PV panel, and moreover during heavy wind and stormy weather, so it can easily damage. The water will be deposited over the surface of the solar cell, so then again it can short circuit any of the the solar cell. Then ultimately there is a problem of that hotspot, or due to the non-uniform current flows between the two diodes in the series, so that also causes the circulating current. It may easily damage the devices due to hotspot. So that is what the reliability study is also very important, and the degradation studies are also very important in this the PV array. And another area of research also nowadays, many of the researchers are actively working on improvement of the solar cell efficiency by using bifacial solar cell. So what the bifacial solar cell it implies, this is basically a monofacial. So monofacial means that the cell, solar PV cell is embedded on top of the plate, right? So top of the panel. So when this is exposed to the sun, then there is an energy harvesting due to photovoltaic effect. But so on the bottom of the plate, there is no formation of the solar cell. There is no embedding of solar cell. So the bottom plate just provides a mechanical strength. But nowadays, the PV panel is fabricated with the bifacial solar cell. So bifacial solar cell means the solar cell is fabricated on both the top as well as bottom of the plate. So now, if it is a bifacial, once it is exposed to the sun, Then the top plate, it is exposed to the sun, so it harvests electrical energy. And the bottom plate, when the sun is falling on the surface also or on the floor, then the floor, if it has the property of reflecting the irradiation, so when the floor is also exposed to the sun, so then due to reflection with a kind of a floor like the Western countries, so during heavy snowfall, the floor with the heavy snowfall is is an important property for reflecting the irradiation. So when the sun is falling, the large amount of irradiation can be reflected with the help of what is called this the snow. Then that will be reflect towards the bottom of the plate, so that also contribute for energy harvesting, so that the total power production would be the combination of both the top plate as well as the bottom plate. That is what the solar cells are basically. A bifacial solar cell, but still it is under development. To install and functioning that such solar cell is still under development. And the basic characteristics, as I told you, basically the solar cell converts light energy into electrical energy, as the maximum current flows when the voltage is zero, and the maximum voltage appears when the current is zero. So multiplying the current and voltage at this point, we extract the maximum power, right? So because this is basically an highly unregulated curve, you might be knowing, because input parameter is a temperature and irradiation. So these two key parameters can change at any time, because it depends on the sun energy. So ultimately, due to seasonal variation or due to climate change, obviously the temperature and irradiation changes rapidly. So due to variable input parameters, and obviously the output power of the PV panel, it varies. That is what it has an intermittent characteristic. So you cannot forecast the sun energy. So that is the difficulties encountered in installing a solar PV panel. Right, so the temperature is very high, then what happens, then the open circuit voltage, it reduces drastically, so then the power production will be affected. But when the irradiation is very high, then the short circuit current is very high, so we are able to generate the maximum power. That is why solar cell, it works, it produces, it produces high efficiency at high irradiation and low temperature. Any solar cell that should not be exposed to the high temperature, then it affects the performance of the solar cell, right? So as this point is highly intermittent, as the curve is highly intermittent, as a nonlinear, so extracting maximum power is very difficult. So that is why we always use a power conditioner system, right? So power conditioner is a device between the solar PV or the PV cell and the load, so that with the help of this power conditioner, we can virtually change or twist or shift this curve, at which we can extract the maximum possible power. That is what the corresponding control is called the maximum power point control. So you can use the power conditioner as a maximum power point tracker. We can be able to track maximum possible power. That is what. So as you use the resistance of 0.05 ohm, so this has to be matched with the internal resistance of the solar cell, so that we can extract maximum possible power. In that way, it satisfies the theorem what is called a maximum power transfer theorem. So you have to use that device. That device can be used to match the load resistance with the source resistance. So that is what we can use any kind of the chopper circuit, or as it is a variable resistance similar to a transformer and AC circuit. So that this point can be easily make it in the equilibrium state, then you can extract the maximum possible power. Right. So according to Ohm's law, that the current would be V by R, where R is the characteristic resistance. It's about 0.05 ohm. Right. As I told you, the current is largely affected by the change of insolation. I told you the current is directly proportional to intensity of solar irradiation. So as the open circuit voltage is having logarithmic relations with the irradiation, right? So when the irradiation changes and the current changes rapidly, right? So now what happens, as the solar cells are connected in series formation for required power. So if the solar irradiation is not uniform throughout the panel or throughout the plate, then you can find that there is a non-uniform irradiation. It causes changes in the current flows between the PN junction or a solar cell. Then due to the different current flows in the solar cell, then it causes the circulating current. right? So that circulating current, it causes unnecessary hotspot and the PV cells, so it may easily damage the device. So that is what many of the cases we use the bypass diode, so that the circulating current can be blocked, so that the current flowing toward the each solar cell remains same, so that we can avoid unnecessary hotspot. So this may be also cases due to the partial shading as well. That is why during partial shading condition, extracting the power at a constant current is very difficult. That is what many of the researchers, they work in the area of maximum power point tracking of the solar panel. You can go through you can go through the recent literatures. You can find more than 200 algorithms that has been proposed by the different researchers and to extract maximum possible power. As I told you that the efficiency of the solar cell, it largely depends on the temperature. So as the temperature increases, then the solar cell efficiency degrades, because the model temperature, it largely affects the open circuit voltage, right? And especially the crystalline monocrystalline cell, still the efficiency is good, and you can up to 17%, but the amorphous cell, it's about maximum of 9%. So most widely we use a silicon cell for electrical power generation, but still 0.4 to 0.5% decreasing per degree, but here 0.25% decrease per degree. So most widely we use a silicon solar cell with this monocrystalline, and moreover the model must be cooled by a natural ventilation. As I told you, it performs well when the temperature is low and the radiation is high. And the resistance effect, as you know, the PV solar cell is the basically built up, made up of PN semiconductor diode with heavily doped depletion region. So ultimately, it has an the parasitic element in the contact as well as in the metal contact, called the resistance, series resistance, and parallel resistance, right? So it also basically a lossy elements, and it also takes a part of the power from the input, so that it affects the performance of the solar cell. So that is basically series and shunt resistances. So while designing or while studying about the mathematical modeling of the solar cell, so ultimately care should be taken to define the series as well as shunt resistance. And let us come to the, till we discussed about the fundamental characteristics of the solar cell. I think you might have understood what are the different parameters involving in the solar PV cells, and what would be the physics behind this solar cell, energy conversion, and also understanding the concept of the efficiency as well as the maximum power point tracking. And let us come to motivation about the research and what we have done. In a grid connected solar PV system, and design and operation of the power converters to achieve high efficiency for different power configuration is a key consideration. Because as you know that basically the solar cell is a non-linear element, and moreover it has an inherent intermittent characteristics, because as we are converting light energy into electrical energy, so the light energy is variable, and again it depends on the the level of the sun. So due to varying temperature and irradiation, then obviously the power output varies due to variation of the output current as well as output voltage. So that is what it always generates an intermittent power, and it always generates a variable output power. So due to the variable output power, that cannot be directly connected to any electrical load or directly connected to any electrical grid. Ultimately, it is they do not accept the variable output power or the variable current with voltage across any kind of load. That is why we have to use a power converter, because as it has an intermittent characteristics that cannot be directly connected with the utility grid, we have to use a power electronics converter. So power electronics converters are playing a very major role to integrate a solar PV system with the utility grid. All renewable energy sources are intermittent in nature. It has an inherent the variable output power. So this cannot be directly interfaced or interconnected with the utility grid. We need an integrating or interfacing device called the power electronics converter. So power electronics converter, it provides an asynchronous interface between the solar PV system and the utility grid to integrate or to feed power to the utility grid. Right. So this cannot be directly connected with. Then what would be the role of power converter? As it provides an asynchronous interconnection, it has to meet the certain requirements. So that the grid connection requirements include maximum power extraction. As I told you, the energy conversion, energy conversion is not efficient in the solar cell. Its efficiency is not even 20%. So you need to use the power converter to extract maximum possible power so that the running cost would be reduced and the high efficiency. So the power converter that bridges the renewable energy source with the utility grid, and it has to, provide a power source with high efficiency so that the stages in the losses in the stages would be very less, and it has to provide a controllable, power that should be injected into the utility grid in terms of active as well as the reactive power, and it should inject sinusoidal current into the utility grid, because as we use the power converter as well as the the intermittent nature of this PV source, so always the output power varies mean that the grid current as well as grid frequency as well as grid voltage it varies while inverting DC to AC, right? So it has to always inject sinusoidal current into the utility grid. I mean the THD should have an excellent transient response, because and as we use the power electronics converter, it has to improve the dynamics of the entire system, so that so that any abnormals or any unbalanced load which is to be connected at the point of common coupling, it has to ensure an excellent transient response even during fault condition. And moreover, it has to have a good synchronization. It's very important to extract the fundamental component for providing a control algorithm. So consequently, the performance of the converter connected to the grid, it largely depends on the control strategy applied. So how the control strategy proposed on this power converter, so that we are able to achieve or we are able to meet these above set requirements called grid connection requirements or grid code compliances. So, and if you talk about this grid code compliances, that varies country to country. And talking about the Ireland, they have Irish grid code compliances. In Denmark, they have a Danish grid code compliances. And Canada, they have a Canadian grid code requirements. And US, they have a US grid connected requirements. And the Chinese, they have a Chinese grid code requirements. And UK, they have a British grid code requirements. So all countries, they have their own grid code compliances while integrating solar PV system with utility grid. Similarly, in India, so we also, the stage of developing, the grid code compliances for integrating solar PV system with utility grid. So this is our heart of the research and what our team is working actively. Integrating solar PV system with the utility grid. We largely working on this control, on the power converter to meet the objectives. So, in this presentation, the objectives of the research it include to design and developing and implementing a grid interactive solar PV system. As the grid interactive solar PV system is developed as a laboratory prototype with the help of three-phase four-legged inverter. Basically, it is a power. It is a grid interactive power converter is designed and used for the PV system. As the control strategy has been employed on this three-phase four-legged inverter, for meeting the above set grid connection requirements. So that includes, controllable active and reactive power into the utility grid, and it also serves as an active power filter for power quality, because whenever you connect a nonlinear load at a point of common coupling, basically as it is interacting with the source of the grid, then the grid current is distorted. So due to distorted grid current, and it degrades the power, norms for power quality, and moreover, if any additional loads are connected, and also it affects the performance. So we have to take an attempt to mitigate power quality problems, to mitigate the lower order harmonics presence in the grid current whenever a non-linear unbalanced load is connected at the point of common coupling, right? So as the control algorithm implementation, it purely depends on the reference current generation. So again, accurate generation of the reference current, again it depends on the fundamental current extraction, right? So for extracting the fundamental frequency component of the AC grid, we use phase locked loop, right? As here we propose an adaptive phase locked loop to extract the fundamental frequency component to generate the reference current accurately, so that with the help of reference current generation in an accurate manner, we can implement the advanced control strategies so that overall objectives are going to be met. Right, the proposed system, it also provides a power quality improvement features such as the source current harmonic suppression and low reactive power compensation and zero sequence current harmonic compensation as well. Because here we used a three-phase four-legged inverter, usually any two-level three-leg inverter composed of six switches in the three leg, right? So we uses the fourth leg as well in three-phase four-legged, so that the fourth leg, it provides an alternate path for path for neutral current, so that the neutral current flow can be suppressed in the neutral wire itself, so that we can neutralize the zero sequence component. So that's the key component for third harmonic current generation, right? And not only that, it also contribute for active power sharing, because in addition to the grid, so PV also can contribute certain amount of power to meet the load demand, so that it also can provide an excellent energy management system. And the function of power electronics in the utility, as you might be knowing, and as an electrical engineer, you should feel proud that we are working in power electronics related areas, you know. So in the 21st century, the power electronics is created great impact among the scientists or the researchers to work in this area for almost all applications. As an electrical engineer, you can't imagine today's power system without power electronics, right? And still we use a mobile phone, and we use power management ICs on the mobile phone, and provide a proper power distribution inside the mobile phone, and you have a variety of memories and the RAM, ROM, and the motherboard and the display, and we need different power level, the different DC power level on the mobile phone. So we use the concept of electronic power distribution system with the help of power electronics, right? Because around 60% of the power, 60% of the investment in mobile is devoted to the power supply, including battery, right? So the performance of your mobile phone, it largely depends on the battery as well as the power management system. So that works under the principle of power electronics. And up to megawatts wind turbine system, we invariably uses power electronics. So talk about all electronic load, your mobile charger, and your laptop, your smart TV, and the washing machine, and air conditioner, refrigerator, electric oven, and electric heater, and almost we use invariably power electronics. In this 21st century, we can't imagine the situation without power electronics. So power electronics, it's become a part of our life. That is what I used to tell. And Professor B.K. Bose was, I think you all might be knowing Professor B.K. Bose is an eminent academician from University of Tennessee, USA. I think he was an prominent scientist in the area of power electronics. So while I was attending a National Power Electronics Conference and IIT Roorkee during 2010, so he told that in the 21st century, power electronics is going to play a major role. So that is why today what power electronics does in power system. We talk about the microgrid, smart grid, and the smart industry. We talk about the smart home and the smart lighting system. You see how the impact has been created by smart lighting system. We invariably uses LED lighting today, thanks to power electronics. We should give big thanks to power electronics. Because of power electronics, viable energy saving has been done, you know. And with the help of power electronics, there was a huge the energy saving. There is an energy saving potential. There is an energy conservation, because much of world economy is purely depends on the electrical energy utilization, how you are effectively utilize the electrical energy. So that decides the country's economy. That is what. So you do not think much cheaply about power electronics. So no power electronics, no power system, no electrical energy. Obviously, no field of engineering as well as. It's almost it's going to be. The world is going to be exist if you compromise power electronics. That is what such a impact has been created by power electronics. So it provides an asynchronous interface, and providing it. It provides an asynchronous interface between the source and load to meet both load dynamics as well as the source dynamics with the help of suitable controller and the power converter. Right. So as interconnecting to asynchronous AC, we use power trans converter as AC to AC converter or AC to DC converter. or DC to AC inverter, or DC to DC converter as well. It has a different configuration, and accordingly you can use based on the load requirement. And the listing of power electronics is very wide. As it has been used in the distributed generation, like wind power generation, the uses to integrate a wind turbine system with utility grid, and also it invariably used in photovoltaic for integrating with utility grid to meet the grid connection requirements. And the fuel cells and micro turbines, we invariably uses power electronics, and it also can be used in the energy storage. In the 21st century, another key technology is going to play a major role, basically energy storage devices. So energy storage devices are basically a batteries, supercapacitor, superconducting magnetic energy storage devices, flywheel, and ultra capacitor and supercapacitor. These energy storage devices are, it became a prominent component in today's power system, especially as the renewable energy is booming, and energy storage can also be used, to provide uninterrupted power, because the let's talk about the photovoltaic energy conversion system. So photovoltaic system cannot provide power throughout the day, because as it depends on the level of the sun. So sun will be available during daytime, you can harvest electrical energy, but during night time, so the sun is not available. Then how will we provide uninterrupted power? Then we have to use the energy storage devices. It store electrical energy whenever the sun is available, and when the sun is not available, then battery supplies the power to the load, so that it can enhance the reliability of the electrical power supply. And moreover, the energy storage devices are a key component to improve the transient response, and it improves the stability of the grid by contributing the reactive power requirement, also contributing for storing the electrical energy when the grid is under abnormal condition. Right. So it provides an excellent energy management. And also the power electronics applications, as you might be knowing, most of the electrical loads and most of the machines used in the industry is basically an adjustable speed drives, either an induction motor drive, or maybe a synchronous motor drive, or maybe a permanent magnet synchronous motor drive, as we invariably use power electronics for improving the load dynamics, and also it also contributes for the power quality improvement. It configured as a dual feeders or uninterrupted power supplies and dynamic voltage restorers, and still there is another important custom power device called a DSTATCOM for the power quality improvement in the distribution level. And still it can also be used in the transmission system, to transmit long distance bulk power DC transmission. We use HVDC transmission, even for medium distance transmission with the help of underwater or undersea cable. We invariably use DC transmission. So we need to convert AC to DC in the sending end, and again and DC to AC in the receiving end. So we invariably use a HVDC transmission, and also we use patch devices in the transmission as well as in the distribution side to improve the overall system stability, as well as to improve the voltage profile at the point of common coupling whenever the transmission line is subjected to fault. That is what the listing is, almost everywhere, almost everywhere. And even now using for a lighting system, we invariably uses, the power electronics, even the LED lighting, we use the, power converters inside the LED to have a proper power management, also to improve the power factor. And whatever we use power electronics, in this situation in the modern power system, still we have the barriers and challenges to implement the concept of power electronics basic system, and there is a complexity in the traditional power system. Basically, the traditional power system, it uses conventional power generation unit. Basically, it is a it is centralized power generating station having fully coupled dynamics between the generation, transmission, distribution, and consumption. So there is a strong coupling between the voltage and frequency component. So controlling voltage and frequency in an independent way is a difficult task. And moreover, the today's power system or modern power system uses renewable energy sources like solar PV, or maybe a micro turbine, or maybe a fuel cells. So they doesn't have any inertia. The inertia is an important component to damp out any oscillations if the system is subjected to any external disturbances, right? As the solar cell or the fuel cell doesn't have any inertia, basically they are the static DC sources. So any disturbance occurs, it cannot mitigate or it cannot damp out such oscillation, because it doesn't have any inertia. And moreover, So reaching the damp out oscillation, also to improve the transient response is very difficult in the solar PV cells and the fuel cells because they doesn't have any inertia. So reaching the steady state, it takes long time. The response is very sluggish. That is what we use and virtual energy storage, virtual energy system like introducing the energy storage. Even solar PV system cannot be used alone without energy storage. So for especially for the standalone system, we invariably use energy storage along with the solar PV so that it can provide an uninterrupted electrical power to the isolated system and the standalone system. And the local focus of power electronics, as still we concentrate on load dynamics, especially in the industry for adjustable speed drives. Now, the scenario has been changed that the source is also an intermittent, and also it is intermittent energy source, the disposed energy source. So the power electronics has to be used between the source as well as load to improve the dynamics of both. That is what like at UPS or distributed generation or the fuel cells or alternating energy sources, we use power electronics converter for asynchronous interface, and until now only fixing the problem of power distribution happens. So finding the solution finding the solution in a cost-effective way is a great challenge, and energy conversion or improving the power management system with high efficiency is again it is a challenging task. Again, decoupling the voltage and frequency component in the transmission as a generation, transmission, distribution is also a challenging task. That is what, as an electrical engineers, we are actively working in this area to find the solution in a cost-effective way, to find the solution with high efficiency. And that is what still this area is emerging. Right, let us come to a schematic of detailed solar PV system. As the solar PV array is composed of the PV model in the series parallel combination. So as it generates a DC power with the required power rating, so that way that feed power to the grid via power electronics converter. As you told that the power electronics converters is provided an asynchronous interface to integrate the solar PV system with the utility grid, and it has with the different topology as well as the components with suitable controller on this power electronics converter. So we meet the grid connection requirements. So that includes controllable active and reactive power, and improved power quality, and the grid synchronization, and excellent transient response, and the grid synchronization as well. So these all requirements are going to be met by the suitable controller on these power electronics converters, right? And the input and moreover it also contributes for the maximum power point tracking, that as the input energy is a light energy, as it is a state of art to the solar irradiation temperature. As it varies, the output power is variable, so we need to have a converter to provide a controllable power to the utility grid, right? So these power converters, it plays an important role in controlling the power delivery, and at the same time it ensures proper integration between the solar PV system and the utility grid. As according to the topology, basically 95% the solar grid connected solar PV system, it uses the two-stage solar PV system. So two-stage grid tied means, so it has two converters. So this is basically a converter with a DC link. This is called a DC to DC boost converter. It converts our uncontrollable DC into controllable DC by boosting the solar PV voltage to high voltage level, and that can be available at the DC, right? And the DC to DC boost converter, basically a converter always interact with the solar PV. This is what is called source side converter, as it transfer power from solar PV to the DC link. And moreover, this is responsible for maximum power point tracking, as it has low conversion efficiency. Then the available power at the DC at the high DC is to be inverted into AC with the help of three-phase GW voltage source inverter. Then the controllable AC power that can be fed into the utility grid. And moreover, the control algorithm which is being implemented on the three-phase grid tied solar PV system or a three-phase voltage source inverter, that meet the grid connection requirements, right? And moreover, and unbalanced non-linear loads are connected at the point of common coupling. Then whenever such loads are connected, then the grid grid current is distorted, and there is a problem of power quality. And moreover, the voltage at the point of common coupling can be deviated from the reference value or deviated from the rated voltage. Then we should have a controller on this voltage source converter to meet all the requirements. Where this is the impedance of the voltage source converter, and still the line impedance also available here. So with that suitable interfacing inductor of the impedance, so the power can be transferred from voltage source to the utility grid. And now, as the source side, the DC power is available, variable DC power, and the grid side, the constant AC power, the controllable AC power is available. So the control algorithm, which is being implemented on three-phase PW voltage source inverter, it has to handle both the DC power on the input side and the AC power on the output side. So it has a both control variable, I mean DC variable as well as the AC variable. So as this is the converter, it interacts with the grid, and hence the name grid interactive power converter. So this grid converter can operate as a grid feeding device or grid forming device. The main control task is to manage the DC link voltage. As the DC link voltage, it basically balance the power flow between the solar PV and the utility grid. So it has the DC link voltage has to be maintained constant to transfer the power from the solar PV to the utility grid. So this should be maintained constant, right? It has to be stabilized at any cost, and it has to manage the DC link voltage, and moreover, it has to inject and controllably active as well as reactive power to the utility grid. And the third option, maybe it act as a grid supporting device, as it can provide an asynchronous service. It provides ancillary services like a voltage control, frequency control, and the power quality, right? So as the AC power control includes grid feeding, grid forming, and the grid supporting, and on the grid side, it has a AC current control and the AC voltage control. And the input side, it has a DC voltage control, right? So it has to handle both the AC variable, DC as well as AC variable. It has to have an instantaneous PQ power theory based on the stationary reference frame in alpha beta, and in the natural reference frame in ABC, and rotating reference frame in DQ, right? So with this instantaneous PQ theory, we are able to decouple the AC components in terms of DNQ or alpha beta, right? So whatever be the control technique you imposed on this voltage source inverter, it has to satisfy the international standard while integrating solar PV system with utility grid, because the harmonic limits are very important. No sinusoidal current will be injected at any cost. Always it has a lower order harmony, so that has to be rejected in the inverter output itself. So we follows two standards internationally, like a US standard and a European standard called IEC 61000 series. Basically for harmonic limit on the PV inverters, we use IEC 61727 series, and in US and Canada and our rest of the countries, we use IEEE 519-2014 standard, and it stands for the recommended practice and requirements for harmonic control in electric power system. In addition to that, IEEE 1547 standard also can be used for DER with a capacity up to 10 MV. So yeah, but the IEEE standards, it's meant for the steady state, and IEC stands for both steady state as well as transit. Most widely, IEC standards can be used for the industrial purpose, and for the renewable energy sources, the steady state response is it's okay. Then we follow IEEE standard, right? So all of them impose the following conditions regarding grid current harmonic component. You can see the level of the harmonic. In the lower order harmonic, you see the level of discharge limit. So through the total THD of the grid current should be less than 5,000, as per IEEE 519-2014 standard. You please keep in mind that any control algorithm can be developed for a grid interactive power converter, but the care should be taken to inject while injecting AC power into the utility grid, while injecting grid current should be with the THD of less than 5%. Let us come to the control structure. As the control strategy which is being applied on this grid interactive power converter is very essential to meet the grid connection requirements. So that control strategy is basically a cascaded control strategy, as it uses internal current control and outer voltage control. So this internal current control loop is responsible for regulating the grid current, right? Because the grid current has to be regulated and it has to be controlled to inject only sinusoidal current component, because the sinusoidal current component is responsible for actual work in the grid, but other harmonic current should be rejected at this stage. So the internal current control is responsible for power quality improvement to inject sinusoidal current into the utility grid, and it is also responsible for overcurrent protection, because the inverter is designed to, carry the rated current of the inverter, so that the AC power can be fed into the utility grid. So when the grid current exceeds the grid inverter current, the inverter can be damaged due to overcurrent, right? So the internal current control is very essential to protect the inverter against overcurrent. So the control loop for the inner current control has to be designed with a larger bandwidth, so that the response of, or the dynamic response of the inverter would be good, so that it can feed power to the utility grid during normal as well as abnormal operating condition of the grid. In addition to that, it has a outer voltage will be basically called outer DC link voltage control. As the DC link voltage control, it has to be maintained constant while transferring power from solar PV to the utility grid, right? So as it contributes for maintaining the power flow between the source and the load, it is contributing for the active power control, because the active power control is very essential to maintain the frequency. And moreover, the voltage at the point of common coupling, that also has to be controlled, so that it can avoid unnecessary reactive power burden on the grid, so that it ensures the unity power factor operation as well. Right. So other control strategies include the DC link voltage control cascaded with inner power control, or maybe an outer power loop cascaded with inner current control. But most widely we use cascaded control on this voltage source inverter with internal current control loop and the external voltage loop. And the architecture for the grid connected solar PV system is composed of the solar PV module that generates a DC power. And then the generated DC power at the low voltage is going to be, stepped up into high DC voltage with the help of a DC to DC boost converter. Then the available power will be, the extracted power will be available at the DC level. So as this boost converter is responsible for maximum power point tracking, then the boosted DC voltage with the PV power will be inverted into AC with the help of three-phase four-legged inverter. Then the inverter output is connected with the utility grid via interfacing inductor, right? So the interfacing inductor is responsible for filtering out the DC current component, which is generated in the inverter current itself. And then you can have a breaker for isolation whenever the grid is under fault, and moreover, the nonlinear or the linear, unbalanced or balanced loads are connected at this point called the point of interconnection and point of common coupling. So for providing necessary control, we need to have a feedback. Basically the signal from the the grid current signal, grid voltage, as well as the DC link voltage, then the PV array, PV current, all will be sensed with the help of sensor. And then basically, and that is basically we use voltage and current sensor, so that has to be interfaced with the interfacing called DCS 1104. Then it is able to generate the digital PWM pulses, and that will be inverted with the help of digital to analog converter. Then the analog signal will be given to the actual driver circuit, so that actual driver circuit can be able to generate the PWM pulses, and that will activate the respective switches, so that we are able to convert the controllable DC to controllable AC, so that we can meet the grid connection requirements. In this way, and the solar PV system can be integrated with utility grid. And each system has been designed. Basically, it has a control circuitry as well as subsystem. Power circuitry. So power circuitry design including the solar PV array, and the solar PV array, as we have taken 13.5 kilowatt solar PV system. I'm sorry, that case would be small. And the 18 PV module can be connected in series to have a rated voltage, and the 3 cells connected in parallel to have a rated current, so that this can be, the solar PV array can be designed for 13.5 kilowatts power generation, DC power generation. Then for transferring this DC power, the DC link voltage is very essential, as the energy can be stored in the form of DC. Then as it transfer the PV power of 13.5 kilowatts, and moreover the boost converter is boost the voltage from 540 into 690 volts. So the DC capacitor has been designed with the 2257 microfarad. And assuming that the DC voltage is about 690 volts. And with the DC bus terminal voltage, the DC voltage has to be designed with the 690 so that we are able to invert 690 volt DC into 415 line to line, right? Because we use a pulse width modulism, so effective utilization of DC link is not good. So the effective utilization would be around 78.5%. So we have to set the DC link voltage would be around 690 volt. And the design of coupling inductor is very important. So the coupling inductor, it is responsible to filter the DC component presence in the DC inverter output. Because if any, if any DC link voltage or if any DC component presents the inverter output, then the DC current it can affect the performance of the interfacing transformer, because the transformer core can be saturated due to the DC component. It also increases the iron as well as the copper loss of the transformer, then the overall efficiency will be reduced. So the interfacing inductor can also act as a low pass filter to filter out the DC current component. That has been designed with 3.31 millihenry. And the parameter calculation, so that it is boosting the solar PV voltage of 540 to 690. So it has been designed with a 2T ratio of 0.21. And moreover, the filter, the boost converter inductance is designed with 4.52 millihenry. So yes, now let us come to the control scheme. As we are implementing a control strategy on this grid interactive power converter, so that control, it has to handle both the DC as well as AC variable. So input side DC variable and output side AC variable. So it has to have proper coordination while converting APC to DQ. So we use the power transformation for transforming that AC quantities in, because AC quantity in the orthogonal quantities, so that we use the power transformation so that the output would be in terms of ID and IQ component. Basically, they call the orthogonal components or DQ components. So the ID component is basically represents the active power current component, and IQ is basically represents the reactive power current component. So it composed of average DC and oscillating AC, right? So that then that as it is basically orthogonal component, they are orthogonal with each other, right? So this oscillating AC component has to be nullified during the transformation. Further, that ID component is responsible for active power component, so that is responsible for the only fundamental component. But whenever there is a power transfer from solar PV system to the utility grid via any power converter like a DC to DC or DC to AC converter, and always there is a power transfer due to the double frequency current component. That double is basically due to 2 omega oscillations or 2 omega component, that is called a double frequency oscillation component. So that has to be rejected. If not, your DC link voltage, DC link capacitor may be damaged due to the overheat or due to double frequency oscillation. So we use a second order low pass filter to filter out such double frequency oscillation with the cutoff frequency of 5 Hz, so that to decompose the DC component and active component of ID. And this is the control strategy as the BVRIT, with the output is given to the boost converter, and the boost converter output is available in the DC link capacitor. Then the DC power will be inverted into AC with the help of voltage source converter through interfacing inductor. Then the active power or controllable power is injected into the utility grid. So the point at which a non-linear load is connected, PCC, right? So when a non-linear load is connected, then the current is getting started. So we propose a control algorithm. So as it has an internal current control and outer voltage control. So the outer voltage control is basically DC link control. So it DC link voltage control, it usually regulate the DC link voltage. So the actual voltage is, with the low pass filter, we filter double frequency oscillations, and we have only the actual DC voltage component, and that will be compared with the reference voltage at 690 volt. Then the error will be given to the error is responsible for to generate the ID star, as it is contributing for active power control. So then the ID star will be generated based on the outer loop control. In the meanwhile, as we also sense the three-phase AC voltage, Then this is responsible for the reactive power control. So during unbalanced condition, then there is no need of any reactive power support. So then the IQ is basically zero. But whenever there is an unbalanced load is connected, then there is a flow. There is a need of reactive power to improve the voltage profile. So this IQ is responsible for the the reactive power control, and ID is responsible for active power control. But both components are orthogonal with each other. Then that corresponding ID and IQ component is going to be transformed into ABC, and so that we are able to generate the reference current. So once the reference current is generated, ISR star, ISY star, and ISB star, then that will be, compared with the actual three-phase AC current, then the error will be generated, right? So the quality of the controller or the performance of this current controller, it largely, it is, the quality of the, control strategy, that purely depends on the reference current generation. So if it generates the reference current very accurately, then the control algorithm is excellent, right? So in that way, we generate the reference current, then the error will be given to the any current controller, so that it can, it can control the current instantaneously, so that the required pulse width modulation PWM signal will be generated, so that will activate the switches, so that we are able to, invert DC to AC, so that AC will be injected into the utility grid. This is the control algorithm. This is the corresponding CT matrix while transferring DQ to ABC. And during balanced condition, there is no neutral current flows, because algebraic sum of all three phase current is equal to 0. But when it is unbalanced, then there is circulation of neutral current, so that has to be neutralized. If not, it provides, it inherently generates the third harmonic component, which is superimposed upon the fundamental in the grid current. And as you need the, the phase locked loop to estimate the theta. You see here the sin theta, sin phi, and cos phi components are very essential while transferring ABC to DQ or DQ to ABC. So that this theta, this phi generation is basically what is called a unit vector generation, as sin phi, cos phi template generation. So that we use a space locked loop, and that will extract the fundamental frequency component of the grid current, so that we are able to generate the unit vector. In that way, we are able to convert ABC to DQ and vice versa, right? And moreover, this sin phi is very important for grid synchronization as well, as it is extracting the fundamental current component. So the quality of control, it largely depends on the reference current generation, and again the quality of reference current generation, that duty depends on the fundamental current extraction. So it composed of the phase detector and the loop filter and the voltage controlled oscillator. So it has to be designed properly, so that we are able to extract only the fundamental frequency component. So as the instantaneous AC voltage, it composed of the R, Y, B, and R3 phase component. And the DC side controller, bus voltage regulation is very important, because it is contributing for active power control. So then the actual DC link voltage will compared with the reference voltage of 690 volt. Then error will be given to the PI controller, that includes the compensator and limiter and the proportional gain. Then that will be providing a proper controller in the closed loop phase. So the care should be taken while designing this controller, including the gain calculation for KP and KA. Accordingly, this control loop it works, so that you are able to regulate the DC link voltage. So the DC link voltage regulation is very essential to maintain the power flow, so that the frequency can be regulated. And this is a corresponding transfer function by taking the ratio between the actual DC link voltage and the reference DC link voltage. So this control loop has been designed, and accordingly the gain has been calculated. So to tune accordingly, the DC link voltage has been controlled. And the 4 voltage regulation, as you are inverting 690 volt DC into 415 volt line to line, so the 3 phase AC voltage should have only the fundamental component, where H is assumed to be 1, and it should be a RMS value of 450, right? So the power balance, as we are inverting, act as a sending unit, as we are transferring power from the inverter to the utility grid via interfacing inductor, right? So it can be, modeled as a power system, that it has a sending end and receiving end. We transfer the power through line reactance, right? So this is the power expression while you are transferring power to the inverter and the grid, and it has a phase angle difference of delta and 0, so that power can be transferred from inverter to the utility grid, and that it is inversely proportional to the line reactance, so that has to be designed with a very low end. And we proposed the incremental, we have studied about the incremental conductance method on this DC to DC boost converter side to extract the maximum possible power, right? As it is, as the name suggests, incremental conductance method. So according to the characteristic curve, the change in current with reference to change in voltage, that must be always zero. It implies that this point is at the equilibrium state irrespective of the temperature and irradiation variation, so that we are the point always extract the maximum power, right? So this slope must be will be shifted downwards or upwards. That depends on the change in current with reference to change in voltage. So if the change in current with reference to change in voltage is greater than zero, mean it is a negative slope. At if the change in current with reference to change in voltage is greater than zero, means the slope is negative. So this is the negative slope, is the positive slope. That depends on the change in current with reference to change in voltage of the PV panel. But at the equilibrium state, this change in current with reference to change in voltage must be zero. So this point should be shifted either upwards or downwards, that corresponding to the duty cycle generation. So at this point, the duty cycle will be generated, so that the concerned switch in the boost converter will be on and off, so that we are able to extract maximum possible power. And this is the laboratory prototype of a three-phase grid interactive solar field system, as it composed of the power circuitry as well as the control circuitry. So it is not easy to design this laboratory prototype in 6 months or 1 year time. Ultimately, you should have funding, as well as you should have a very dedicated, hardworking scholar, so that he can be able to completely study and observe each components of control circuitry as well as power circuitry. Then, according to the level of the funding, each components can be procured and designed, so that overall laboratory can be made in the, overall prototype can be made in the laboratory, so that you can validate your simulation results experimentally. And this is the simulation results of the steady state. As whenever, as the pole voltage or the grid voltage remains sinusoidal, but whenever you connect a three-phase diode rectifier load at point of common coupling, then the grid current is distorted, right? Because when you connect a three-phase non-linear load like a diode bridge rectifier load, that it interacts with the source, so that the source current is getting distorted, right? So without any controller, see the response of the grid current, it is basically non-sinusoidal. And now with the help of active harmonic frequency operation of the control, inverter, then the grid current waveform it becomes sinusoidal, and moreover the current changes from 28.6 ampere to 10.66 ampere to observe the dynamics of the study. And throughout the case, and you can see the DC link voltage, it remains constant. It is always tracking the reference, right? So the controller, it ensures the constant DC link voltage, so that there is a constant power flows between the source and the load, as it is a key component to control the grid frequency. And this is the load current waveform, as it is staircase, as we connect a three-phase diode bridge rectifier load, and you can see the compensating current by the inverter, and there is no control strategy applied, there is no compensating current. So ultimately the grid current is getting started. And with the help of the control strategy, and we are able to, we are able to neutral, we are able to, reduces the lower order harmony, so the grid current becomes sinusoidal, and it also interfaces with the three-phase AC voltage, so that the power factor of the grid become unity, right? So there is an improvement in the power factor as well. See the transition of the power and of the supply power, that has been reduces from 20.6 kilowatts to 7.41 kilowatts due to reduction in the load current, and corresponding the PV power, it also becomes 13.49 kilowatts as it's supplied to the grid. And this is the corresponding PV voltage and PV current, and the solar rating is assumed to be constant, and this is the transient response. Now the current reading increases from 34.37 ampere to 15.85 ampere. See the response. See the response, as it has been reduces from 34 point to 15.84. You see the load current is still, it is three-phase diode rectifier load, but throughout the case the DC plus voltage is maintained constant. And moreover, the grid current waveform is in phase with the grid voltage, so the power factor of the grid becomes unity. And see the the level of the power changes, and moreover, see the source neutral current without any controller. The neutral current can be carried by the neutral wire, but with the help of three-phase four-legged inverter with the suitable control strategy, the zero sequence component becomes zero. So it is neutralizing the neutral current. So the third harmonic current absence in the grid current, and see the load neutral current, but still the neutral current it flows in the load, but in the source it has been neutralized. This is the dynamic response during solar intermittency. So due to changes in the irradiation and ultimately the grid current also has been changed, but throughout the case the dynamic response is excellent because the DC link voltage, it follows the reference trajectory of 690 volts, so that it provides an excellent dynamic response and also contribute for this DC link voltage stabilization, so that overall performance has been enhanced. And the grid current waveform, it is in phase with the voltage, and again it operates at unity power factor. And this is the experimental result with the active harmonic frequency operation. So without any controller, the source voltage it remains sinusoidal, but the source current is distorted because of the phase diode rectifier load. So as the controller has been in practice, so that your controller it mitigate low and under harmonic. So your what is called your three-phase AC current will become sinusoidal, and it also contributes for the power quality. Yeah. And you see here, and moreover, your three-phase AC current, it is in phase with the voltage, the power factor become unity, right? And in the meanwhile, see the source current is also sinusoidal, that is in phase with voltage, but still load current still it is a staircase because we connect a three-phase diode bridge rectifier load. And throughout the case, and the DC link voltage or DC bus voltage, it is maintaining constant, right? And the three-phase AC current is highly distorted as we connect the three-phase diode rectifier load, so that there is a strong circulation of the neutral current. But with the help of the controller, the neutral current or zero sequence current component is neutralized, so that this is zero, and moreover, all three-phase AC current it becomes sinusoidal, and it is also in phase with the supply voltage. And as I told you, the supply current is in phase with the supply voltage, and moreover it is sinusoidal, so the power factor become unity. And for all the cases, you can see the DC bus voltage it remains constant, and it is also contributing for the real power sharing, as the real power shared by the grid is grid is 110 watts, and 102 watts is shared by the PV, so that the surplus amount of power can be stored in the grid, about 56.7 watts. And this is the harmonic spectrum of the grid current with and without controller. So without controller, the THD of the grid current was 26.5%, and with the help of the active harmonic frequency operation and the voltage source inverter or the grid active power converter, the THD has been significantly reduces from 26.5% to 4.67%, as it injects only fundamental current component. And further, the multi-purpose operation, or it is a multifunction inverter operation, so it has been reduced to 4.40%. Yeah, this is the comparison table for all the three phase with without controller, and with active harmonic frequency operation, or with multifunction inverter operation. So throughout the study, you see here the load current THD, the grid current source current THD is less than 5%, as it satisfies IEEE 519/2014 standard. And throughout the power factor of the grid, it is almost unity power factor. So that is the beauty of this proposed controller. And this is the the transient response improvement during state change in the non-input load, as the load has been increased suddenly at this point, or the current has been suddenly removed, even during sudden increase in load or sudden decrease in load. Throughout the case, the DC bus voltage is regulated, it is maintaining constant, so that the frequency is within the prescribed limit between 49.5 and 50.2 hertz. Right, see the response here. And for all the cases, throughout the DC link voltage is maintained constant, and the neutral current can also be suppressed with the help of this fourth leg of the voltage source inverter. And this is the summary of experiment in the hardware. And for the experimental validation, we have scaled down the simulation values from 415 volt to 60 volt. The rest of the parameter has been designed accordingly. And we consider the input power of the solar PV panel about 5 minutes. Input power from the solar PV panel about 500 watts. Then accordingly, the experimental results has been validated with the simulation, and we could find the strong convergence between both simulation as well as experiment. And the summary, the multi-purpose voltage source converter to presented control strategy can be made to fulfill the grid connection requirements, to integrate the intermittent solar PV system with the utility grid. That requirements, it includes the source current harmonic rejection by the nonlinear, introduced by the nonlinear load, and it effectively serves as the neutral current compensator with the help of the 4 lag. And moreover, it also injects the sinusoidal current into the utility grid with controllable active as well as and reactive power. And moreover, the power factor of the utility grid can be enhanced to unity. And also, it eliminates the need for supplementary power filtering equipment to enhance the power quality at the point of interconnection. So overall the system performance became excellent with the help of proposed control strategy on this inverter. And this was the study that we have published in IET GTD, IET Generation Transmission and Distribution Journal, which is one of the top tier journals in the Q1 category. And also we worked further on this advanced control strategy that has been made and published in IEEE transactions and industrial applications. And here three-phase overlap inverter shunted across the AC source. So this can act as a shunt active power filter. And the shunt active power filter has been powered by a solar PV via DC to DC boost converter with and power flows in the DC link voltage. So that the control algorithm has been made and studied with the same, the case studies. And here the control strategy has been employed and implemented with the help of DSpace 1104 platform, because once your proposed control technique has been simulated the MATLAB simulating environment, so this can be easily generate the PWM pulses by the interfacing called the DSpace 1104. So you do not require any assembly language to write an algorithm for the relevant control strategy, but here this can be made with the help of MATLAB simulator. So that is the beauty that most of the researchers they use the DSpace 1104 platform for experimental validation. And the DSpace 1104, it's about I think 4 lakhs. It is sold by Dynavision, which is one of the prominent suppliers in India. So they supply this DSpace 1104 digital signal processor. And here what the active current control strategy we made that the feed forward control loop, as it can exactly detect the active harmonic component, so that the control strategy is very accurate for the reference current generation. So this is the way we made this control strategy, what is called active current harmonic control strategy for the each phase. And this is one of the very novel and advanced control technique we have proposed, and that has been published in IEEE transactions. And this is the configuration of DSpace. As you might be knowing, it is like a microcontroller with a signal processor, and that has been made in this what is called in experimental platform. And this is the transient response during TV perturbation. I told you that with the multifunctional inverter, as it acts as a shunt active power filter, it ensures the power quality improvement. Without any controller, the supply current waveform is non-sinusoidal due to introduction of nonlinear load at the point of common coupling. But it becomes sinusoidal because this acts as a shunt active power filter, so that it injects the complementary component of the harmonic current presence in the grid current, so that it shapes the grid current waveform sinusoidal. Right. See the load current response, still it is non-sinusoidal staircase waveform. And the compensating current is supplied by the inverter, so that it shapes the grid current waveform sinusoidal. And moreover, advanced with the feed forward control loop with the outer voltage control strategy, the DC link voltage is always follows the reference trajectory of 690 volts, so the overall dynamic response becomes excellent. This is the voltage, grid voltage, it interfaces with the grid current, so that the power factor of the utility grid it becomes unity. And this is the power scenario, the supply power as well as the grid power. And throughout the case, the DC link voltage is maintained constant. And the DC bus stabilization here with the help of feed forward control loop. And what we proposed here, see the peak overshoot during the state changes in the load, the DC voltage stabilization without feed forward compensation. You can see that the peak overshoot as well as the steady state response is very poor. But with this advanced control strategies, the steady state response is largely reduced. The peak overshoot as well as steady state response is largely reduced, so that the overall system dynamics become excellent. And this is the corresponding experimental result. And without any controller, as we introduce a three-phase nonlinear load at the point of interconnection, see the supply current is distorted and it's like a staircase. So with the help of the advanced control strategy, your grid current becomes sinusoidal and it is increased with voltage, so the power factor becomes unity. And moreover, throughout the case, the DC bus voltage is maintained constant and it follows the reference trajectory of 690 volts. And you see three-phase supply current becomes sinusoidal, but still the load current waveform it becomes staircase and non-sinusoidal. without any controller, see here the three-phase AC current is highly distorted, and hence there is a neutral current, right? Because the neutral current is an algebraic sum of three-phase AC current. As you connect a nonlinear unbalanced load, so there is a circulation of neutral current. Now, with the help of this three-phase four-legged inverter with the multifunctional inverter operation, so the source current it becomes, the neutral current it becomes zero, because it neutralizes the zero sequence component, and moreover three-phase supply current it becomes sinusoidal, and it interfaces with voltage. And this is for the active power sharing. So it also contributes for active power sharing, because the inverter is powered by a solar PV. So it also supplies the additional power to the grid, so that the load demand can be met not only with the grid, it also by a PV. So it also contributes for an active power sharing. And the THD of the grid current without any controller, was about 25.1%. Now with the controller, it has been reduced to 4.7%. Right, and moreover, the power factor it become unity. So and the frequency is almost 50 hertz. And this is the without a multifunctional inverter. So we have tested for the hardware about 143 watts. Now with the multifunctional, active power has been reduced to 60. So it means 83 watts has been supplied by the solar PV. And moreover, the reactive power support on the grid has been significantly reduced from 60 VAR to 5.9 VAR, so that the power factor it become unity. And the grid current magnitude also has been reduced instantaneously from 4.3 to 1.66 ampere. So the line losses are largely reduced, and the grid current EHDs reduces to 4.7%, as moreover it satisfies IEEE 519 2014 standard. So the summary of the proposed research. So the proposed solar PV with multiple inverter feeds the generated real power to the utility grid in addition to the reactive power. And moreover, as it acts as a shunt-active power filter, it improves the overall power quality whenever you connect a three-phase diode bridge rectifier node at the point of common coupling, and it completely satisfies the grid connection requirements of solar PV system. And additionally, the fourth leg of the voltage source inverter is effectively controlled to supply the load current, harmonic, load neutral current demand under unbalanced loading condition. Consequently, this enables the utility grid to deliver only the balanced and sinusoidal current at unity power factor. So the research presented here clearly illustrates that the proposed multifunctional inverter meets the THD requirement of the IEEE Draft 519/2014 standard. And these are the key references. We could identify the problem in this relevant areas, so we could be able to develop a multiple control strategy that is being employed in this grid interactive solar PV system. And I'm happy to announce you that I'm a lead editor for electrical engineering and Springer Journal, which is one of the prominent AC indexed journals since 1910. As I have floated a special issue called energy storage, design, control, and application in modern power system. So, if any of the participants working in the area of energy storage and its applications in power and energy, you are welcome to submit your research manuscript to this prestigious electrical engineering Springer Journal. So the important dates to submit the manuscript is 15 December 2020, and the outcome of your submission will be made 30th March 2021. And if you have any doubt, or if any support regarding this special issue, or want any clarification, you can email me, and accordingly I can clarify your doubts. And all proposed paper must be submitted via editable manager online submission system. While submitting, select specialty energy storage, so that we could understand that you have submitted your manuscript for this proposed special issue titled energy storage design, control, and application in modern power system. Okay. Yeah, thank you very much, dear participants. Really, so it was, the good experience for me to share my knowledge in this grid interactive solar PV system. Hope you might have enjoyed my session. You might have understood how that experimental, work has been carried out in this area.
Babu sir. Sri Babu sir, it's a very good morning.
Yes, sir. Good afternoon. Yeah.
It's a very nice and excellent presentations. Dear participants, if having any doubts, either unmute your audio or direct unmute your audio or use the chat box to interact with the resource person. I think it's having Lalit Patel. You unmute your audio and directly interact with the resource persons. Raise your hand. Lalit Patel. Having any doubt?
Yes, participants, if you have any doubt, please.
Doubts, use the chat box. Otherwise, unmute your audio and directly interact with our resource person.
Sir, I have one question.
Yes, please.
Sir, in grid forming, is grid connected to inverter, sir?
Yeah, please.
Sir, in grid forming operating mode, is grid connected to the inverter?
Yeah. Yes, please.
Sir, in grid forming microgrid operation mode,
Yeah. Please tell me.
is it connected to grid, sir? Output of inverter is connected to grid, or it will be in islanded mode, sir?
Yeah, so during the grid forming device means it is grid connected. Right? If it is a grid feeding device, that is in isolated mode.
Sir, I didn't get.
Yeah, it is. If it is a grid supporting device, that is in islanded mode or in the microgrid mode. Yeah, grid supporting or ancillary services required when the inverter is working under microgrid mode.
In grid forming operation mode, sir. In grid forming.
Yes. During grid forming mean it is with grid connected mode only.
Okay, sir. So in grid feeding, sir.
Yeah, see the grid feeding means what? I mean feeding power. Yes, grid feeding means it feeding power to the grid, right? So it implies that whether load receives power from the grid in addition to renewable energy sources. So if the load receives power alone from the renewable energy, mean it is isolated mode. But in addition to the renewable energy, if it receives power from the grid, mean it is like a grid connected mode. That is what. So the inverter, by default, inverter it feeds power to the load or the grid, right? But the mode it depends. Yes, but the mode depends on the level of the load, right?
Yes, sir.
Okay.
So in grid forming, if it's connected to grid, then how to control the voltage and frequency, sir?
Obviously, see, whatever the control strategy while you are implementing on the inverter, of course, the reference current generation is very essential, and moreover, the load profile can also be tracked, right? So, if it is exactly studying about the microgrid mode or standalone mode, then the control strategies are quite different from the grid connected mode. So, that you please keep in mind that, right? And moreover, once the control strategy being employed on the microgrid mode, then you need to ensure there is a proper energy storage as well. Because during standalone or microgrid mode, energy storage is very essential to have uninterrupted power. So that is what. As you talked about the grid connected, so you do not require any the support from the renewable energy. I mean, sorry, you do not require any support from the energy storage devices. Okay. Yeah.
Okay, sir. Thank you, sir.
Okay.
Dear participant, any other participants? Okay, Dr. Sitibabu sir, it's a very nice and excellent session. Even though your internet connectivity having some problem, anyway, we are successfully completed this session.
Yeah, that is true.
It's having last 2 or 3 days back also. Unfortunately, we changed our slots also during this cyclone formed in Tamil Nadu. Even though it's having successfully, you are took a lot of risk and given the wonderful lecture to our participants. Thanks once again, Dr. Sitibabu sir. Mr. Naresh Kumar sir, please say a word of thanks to our resource person, Dr. Sitibabu from IIIT Kanchipuram.
Yes. Yeah, thank you, Shravan sir. On behalf of Tribute Department BVRIT, I want to say the vote of thanks to Sitibabu sir. Thank you, sir. Thank you for your valuable lecture on the basic scenario of renewable energy and the objectives and the grid interactive PV system and what is the architecture of it and what control algorithms, how you are going to implement that, and what is the hardware setup that is and the experimental results, which are clearly explained, sir, which is very important for the researchers to implement over the research, have a great idea regarding that. Thank you, sir. Thank you for your wonderful lecture, sir.
Okay. Yeah, thank you very much, Dr. Saravanan, and for giving me an opportunity to share my knowledge. And dear participants, hope you might have enjoyed my session. And thank you very much and have a nice day. You please enjoy with the rest of the session. And tomorrow, all the participants, my request is to please, watch this live session and interact with your speakers. That is very much essential, So it is better to ask one questions, then you know the all, right? Thank you very much, and again, have a nice day. Okay, I'm leaving the session.
Thank you, sir. Thank you, sir. Dear participants, the feedback link posted in the chat box, please complete before 1 p.m. today. It's enabled up to 1 p.m. only. The next session will start on 1:30 p.m. We'll meet on the 1:30 p.m. Thank you, participants, for your patient listening. Thank you.